Hello everybody, welcome to the measurement session of the machine dynamic course. In this video I will try to explain you about the measurement setup, the object of the measurement and how we're gonna do. So let's see how it goes. I try to explain maybe general or some details. So what we're gonna measure? As you can see here, we have one rotor. So this is the main shaft of one high-speed electric motor. And the thing that we're gonna do here is measure the natural frequency or free mode of this rotor. Okay. And these are the vibrometer, the laser heads, and this is the whole measurement setup. We will use this vibrometer, which is connected to the computer over there, to measure those frequencies. But we need to first excite the rotor, and because of this, if you can see here, we have one automatic hammer that we can excite or apply this vibration to the shaft. And here we have two laser heads to somehow measure those frequencies. We have one laser head here. It's for a reference point. So basically this is a reference point of the vibration measured with this. And then the larger camera that is somehow go through the whole length of the rotor and somehow get the data from the whole length, not only one point. And here, this is the computer that the whole data comes here as a data acquisition center. So as you can see here, this vibrometer, if I go here is a little bit tight to walk. Okay, this is how it look like. You can see that in this screen we have the whole rotor. So, and these are the information received from this, as I said, larger camera. Okay. I will back to this computer work on how this software works later on. But maybe first discuss about the free mode. You remember in a first rotor dynamics session, you learned that how you can model the one rotor, no matter what is the material, what is the cross sections, and so on. You learn how to model it. In a Robeden package, we have one function to calculate the free mode. And when we are talking about the free mode, it means that forget about all bearing properties and just calculate the natural frequencies of the single shaft. Okay, but in industry it's a challenge to actually make an exact free mode measurement setup, because the free mode means that it shouldn't apply any external load. But here the thing that we did is lift the rotor with from two points with some kind of rigid rope. Okay, basically the rotor is not free in the vertical directions. You can see it's totally fixed with this rope, but in a horizontal direction it can freely move. I don't know if you can see it with this. So basically this rope only stop or apply the constraint in a vertical direction, but in a horizontal one we have really free movement. So as you see, it's something like that. It's really free movement without applying any bearing force. Okay. What else? Basically what it does, these lasers is just, I don't know if you can see it or not. I will try to go through the shaft. You might see those reflection points on the shaft. So first, when it starts, we apply the force, for example with this automatic hammer. The laser, based on this Doppler effect, try to read all those movements on the shaft, and later on generate the natural frequencies of the whole shaft. Okay. What I should tell you more? Maybe I can go to the software itself. The first thing that we should check is we should see that if the automatic hammer works or not. So if I just click on that as a generator on, you might hear that noise, that the hammer starts to excite the rotor. Okay, but still we do not start any measurement. I will stop it, it's a little bit annoying to hear this all the time. But about the software itself, the first thing that we need to do when we want to start the measurement is perform the 2D and 3D alignment of the shaft. So basically what we do in defining the 2D and 3D alignment is define the object that we're gonna measure to the laser heads. So we should define that what is the surface of the object and how large it is, and somehow define different points on a shaft. This is the best way to define, somehow learn the machine what is the object. So, and also make it easier to the laser heads to follow the points. So basically this is the 2D and 3D alignment part. The next part is defining the, I don't know if you can see it or not, maybe, yeah, now you can see it, maybe. The next part is defining the measurement points on a shaft. As you can see here, I defined one row of the points and they are all connected together. So basically maybe about 10 or 15 points defined in the length of the shaft. And yeah, because we would like to see the mode shapes and natural frequencies in a horizontal direction. That's why I defined one line here, but it can be even more lines, but okay, I decided to define only one line of the points to measure. And what will be happen that after each excitation from the hammer, the laser will read all these points individually. So basically if we have 15 points, we need to excite the rotor 15 times, because the laser can go through those points one by one, not all those in the same time. Okay. The next part, it goes to focus on these points. But if I back to the rotor, I will show you that actually I put some reflector tapes. Just you can see those points. I just glue it to the shaft. The reason is the surface of this rotor is quite somehow shiny, and it's not so good for a laser head to receive the maximum reflection. So that's why I put those tapes. And if I go back to this, the end of this, you can see that these are the signal level, and now it's maximum because I just point those to the place that I already put those reflector tapes to receive the maximum reflection. Okay, what else? If I back again to the software, another place is defining the acquisition setting. For example, in a general part, it asks us about the how many times, or if we want to do this kind of averaging out of the data, you can define that, for example, for each point, how many measurements you want to do. It's always good to have, for example, at least average of 3 measurements for each point. Then you will receive much more accurate results. The next part, okay, we have some channels. We need to define the reference points. As I said, one of those laser heads is about the reference points. These are the filters for signal processing. I will not do anything then. The frequency range. Okay, I assume that I'm interested to those frequencies, all natural frequencies between 0 to, for example, 3000 Hertz. And here in this place we can define that how many points, FFT lines. Okay, maybe this one also is not so important to know, but how accurate we want to measure. These are the windows again for data somehow signal processing. Here is a trigger, how it start to, what is the source of this triggering. So I just define the reference 1. This is the laser, one of those laser heads as a trigger point. Okay, and the vibration range, millimeter per second, how large should be, we can decide. And then the information about the generator. So what should be the applied force and also the frequency of excitations. Okay, but maybe I can do one set of measurements. For example, I will not go through all those points because it will be somehow lengthy. So I just select one point, start the excitation, and try to measure one point. Okay. Okay, this figure shows those frequencies. As you can see here, in this range, this is our first peak. The frequency is about 714. The next peak is about 900 something. At the end, about 2500, we have another frequency, and this one is about 3000. This is our fourth mode. Okay, let's stop it for a while. Okay, maybe another round measurement round, almost at the end of the rotor, and see how the mode look like. Okay, this is not a so good point to measure, but I will go through this. can see that all these amplitudes are changing according to how good we excite the rotor. Okay, so these are the information for only one point. But if I want to go through the whole points that we define, it takes maybe about 10 minutes. But I did it beforehand. So if I open my previous measurements, okay. Basically, when you open those, when the whole measurement has done, it will save the data in this format. How it look like? Okay. So I just go here, don't care for a while. But you remember also for one single point, the detected frequency was about 700. Now still we are in a 700 range. Okay. But how we can be sure that this is the first frequency? So the place that we can understand that we be sure that this is the first frequency is a mode shape. And if I just run this video, you can see that this is really similar to the first mode shape. I don't know how clear it is, but yeah, this is the first mode. And if I go to the click on that, so it will change the video to show you the second mode shape, and it's exactly like the second mode shape. So if I want to open the paint, for example, to draw you, let's see how it works. I'm not so good in a... Okay, so if this is the rotor, so if the first mode would be like, oh no, if this is just a rotor, usually the first mode should like similar to this. Oh, I don't know how to run. So this is a shape of the first mode. And if you back to this software, if I go to the 700, you can see that the same mode it has repeated. So the second mode also, this is the second mode. And if I go to the higher, okay, this is little bit mess, but if we just assume that just connect those lines really smoothly together, you will notice that this is the third mode. Okay, these are the whole information I want to tell you. But okay, as I said, that this is when you connect all those points, and this is the average frequency out of all those points. But I can also go to this instead of this average spectrum, I can go to the single scan points. So then it gives us all those information individually. Okay. Okay. Now I'm going to just see the result for the end point of the shaft. You can see that the first mode is quite clear with a really high amplitude, and the second one is a little bit smaller. But if I go to some points, for example, in the middle of the shaft, you can see that the first mode is still clear, but the second mode is almost died. So it's really small amplitude. And this is the thing that why the mode shape is important, because if I go to the first mode, if I go to the second mode and see the video of the second mode in the middle of the shaft, you can see that the second mode in this point has the minimum amplitude So that's why this point, if we are interested to see this excite the second point, the middle of the shaft is not a good choice, because basically it doesn't have any deformation in this point. It's a node. This is another important analysis I want to show you, that which points can excite with a different amplitude. You can see that the end of the shaft, it goes up and downwards with a really large amplitude, but in the middle it's almost zero. It's for a second mode, but again, if I go back to the first mode, you can see some deformation in between. So it's not a bad point to measure the first frequency. So, and that's why having the full analysis in the whole length of the shaft is important. Then we can make an average and connect those points together, and when we plot it according to the average spectrum, average data, we will be sure that we can detect the natural frequency or flexible modes. Okay, but if you go to the initial points, in a lower frequency also we have some vibration. So if I zoom to that area, you can see that we have some peaks also here. But what does it mean if I just go to those points? And see the video. You can see that it's almost like a rigid body mode. The shaft goes like this, or go upward and downward, but all those, they are in the same mode. So that's why these are a rigid body mode. But the first critical speed, or the first flexible mode, sorry, it's here, about 700, that the mode shape start to behave like this. Okay, I hope that you learned something out of this video. It's especially for students who cannot participate in a measurement sessions, but I hope to see the others in those measurement sessions that we have. Okay, good luck.